Welcome back. Today we are going to see about blockchain transactions life cycle. In this, I'm going to show you an example of simple transfer from wallet A to wallet B. Okay. So far we have talked about hashing, blocks, mining, and consensus as a separate ideas. In this video, we zoom out and follow one transaction to start to finish. Every stage it passes through before it's a permanent, unchangeable line in the ledger. By the end, you will be able to point to exactly where a transaction is at any moment and explain what that matters. Now we are going to see about the journey of the transaction lifecycle. Here is the whole trip in one glance. There are 7 stages: creation, broadcast, mempool, validation, selection, propagation, confirmation. We will use one running example the whole way through, sending funds from wallet A to wallet B. Keep an eye on where that one transaction is at each stage. It's easy to lose track once the network gets involved. Before starting to that, I'm going to ask you one thing. At which of these 7 stages do you think a transaction is first considered irreversible? Think of it and take a guess. We will see it properly at stage 7. Next, we are going to see about how to create a transaction. Everything starts inside a wallet app, not on the network. The wallet assembles a message with its fields: sender, receiver, amount, or nonce. That's just a sequence number that stops the same transaction being replayed twice. A key, and finally a digital signature. That signature is the important part. It's produced from the transaction data plus the sender's private key, and anyone can later verify it using the sender's public key without the private key ever leaving the wallet. One thing to stress here: at this point, nothing has left the phone or laptop. The transaction is just a signed piece of data sitting locally. It only becomes the network's concern the moment it's broadcast, which is our next stage. Now we are going to see about broadcasting to the network. See the picture. Now the wallet sends this signed transaction to one or more nodes it's connected to. From there, it spreads by gossip. Each node that receives it passes it on it to its own peers, who passes it to theirs, and so on. Three things worth remembering in this broadcasting to the network. There is no central switchboard directing this traffic. It's peer to peer and deliberately redundant. It's typically fast. A well connected network reaches most nodes within a few seconds, and every hop double checks. A node only relays the transaction onward once it has passed that node's own basic validity checks. Next, going to see about mempool. Every node that receives a valid transaction places it into its mempool, short for memory pool. Mempool is a short name of memory pool. Think of it as a waiting room for transactions that haven't made it into a block yet. Notice the ordering. Transactions are typically shorted by fee, highest because miners and validators are economically motivated to include the most profitable transactions when they build a block. For example, transaction B sits second here, a moderate fee, a moderate weight. The mempool is local, not global one. Every node keep its own copy, and those copies can differ slightly depending on what each node has seen and its own filtering rules. If transaction, now I'm going to ask you one question. Think of it. If transaction B sender has set a very low fee, what would happen to it during the busy period? Like if you sit in a mempool longer, possibly for hours, as higher fee transaction keep jumping ahead of it. Now we are going to check the validation. Before a transaction is relayed further or picked for a block, it has to pass the same book at every node. This is meant correct. I mean right fields, right size. Does the signature verify against the claimed sender? Is there no double spend? Meaning these exact funds haven't already been committed elsewhere. And is there sufficient balance to cover the amount plus the fee? It will fail even one of these checks and the transaction is simply dropped. It never reaches a block and the sender would need to fix and resubmit it. Now we are going to say about selection for a block. How we are going to selecting a block. Sitting in a mempool doesn't get a transaction into the ledger. Someone has to actively pick it. How that happens depends on the consensus mechanism. Under proof of work used by Bitcoin, miners race to solve a computational puzzle, finding a valid number. Whoever solves it first earns the right to propose the next block and collects the fees plus the block reward. Under proof of stake used by Ethereum, since the merge, there is no race at all. A validator is chosen, often semi-randomly and weighted by how much cryptocurrency they have staked, to propose the block. Either way, the winner assembles a candidate block by pulling transaction out of their mempool. Usually highest fee first and transaction B finally gets its chance to be included. Now, block propagation and consensus. The newly built block doesn't just sit with the proposer, it gets broadcast to the whole network using the same gossip pattern as stage 2. Every node receives it, re-verifies everything, every transaction inside, plus the block's own rules like size, limits, proof of work, or proof of stake, and that it correctly points back to the previous block. If it checks out, nodes extend their chain with this new block, immediately start working on the next one. One edge case worth flagging. What if two valid blocks arrive at almost the same time? That's a temporary fork. The network resolves it using longest, or in a proof of stake terms. The heaviest is chain rule. Whichever branch keeps growing fastest is the one nodes evenly settle on, and the other branches transactions go back to the mempool to try again. Now confirmation and finality stage. Our transaction is now inside block N, but it isn't done. Every block mined on top of block N is more confirmation, and each confirmation makes the transaction harder to reverse. For Bitcoin, the common rule of thumb is about 6 confirmations, roughly an hour before treating a transaction as settled. That's called probabilistic finality. Technically irreversible, just astronomically expensive to attempt the deeper it gets buried. Ethereum, after the merge, works differently. After about 2 epochs, roughly 13 minutes, a block becomes finalized. Reversing a finalized block would require validators to probably violate the protocol, which gets their stakes slashed. That's economic finality backed by a direct financial penalty rather than just computational cost. Now, think of it. I have asked you one question in slide 2. So, back to that question from the start. A transaction isn't irreversible, that is, instant, it's mined into a block. It becomes practically irreversible gradually as confirmation accumulated. Let's zoom back. Create and sign, broadcast, sit in the mempool, get validated, get selected for a block, watch the block propagate, and finally accumulate confirmation until it's selected. End to end, the first intrusion typically takes seconds to couple of minutes. Reaching a widely accepted confirmation that takes several minutes more, depending on network condition and the fee you offered. These are the key takeaways. Four things to carry forward. A transaction earns its place on the blockchain gradually, not instantly. Validation isn't a one time gate, it's repeated at every relay, at block building, and again by every node that receives the finished block. Fees are a real lever. They influence how quickly you move through the mempool, and confirmed is a spectrum, not a switch. This is the life cycle of a blockchain transaction. Hope you all understand it. Thank you.